welcome to this video. Here we're going to learn how to solve a problem kind of like number 12, or exactly like number 12, from the worksheet. This is another rotational equilibrium problem. We have here a bar which is hanging down. The mass of the bar is 5 kilograms, and so that weight, the force of gravity, acts at the center of mass of the bar. So right there we have a force equal to 5 times 9.8. In addition, there's a block which is hanging. Now this block is 15 kilograms big, so the block is hanging down at the very edge, and it's pulling down with a force of 15 times 9.8. Its weight is exerted on the bar at the very edge. The length of the bar is L, they say in the problem. So this here, that length is L, and let me try that again. And what else are we given? We know the angle right here, this angle, is 25 degrees, right? Which is also the same as that angle. It's the angle between L and the rope. So the rope is the last thing shown, and the rope has been stretched, so there's tension pulling up along that angle. Okay, in addition to those three forces, right? So far we have three forces, 1, 2, and tension is the third. The bar is being pushed up at its leftmost edge by this ledge right here. So the ledge there is pushing the bar up, and then the wall is pushing the bar farther or to the right. So the wall is pushing to the right like this. Let me see if I can use a different color. Blue. So in blue there is the force of the wall. Now, we have two conditions. There's rotational equilibrium, and there's also translational equilibrium. So the bar's not moving. The first of those, rotational equilibrium, says that the net torque is 0. In other words, if we add up all of the clockwise torques, they will be equal to the sum of all of the counterclockwise torques. Sometimes I write the sigma, and sometimes I just kind of leave it out. I don't typically write the absolute values, we just remember that those are there. Okay, so I'm going to choose as my pivot point the leftmost edge of the bar. I'm going to choose this point right here. Let me do that in black. That's the pivot point I will use. And I'm going to balance the torques about that point. So, what's pulling clockwise? Clockwise is this way. There's the 15 times 9.8, there's that force. So 15 times 9.8. That force is exerted at a distance L from my black dot, from the pivot point. And that force is at a 90-degree angle, so we have the sine of 90, which is 1. And then in addition, there's the 5 times 9.8, there's the weight of the bar itself pulling down, just like the block, trying to rotate clockwise. So there's a second term on the left side. I have the 5 times 9.8, and how far away is that exerted? It's exerted at half the bar's length, L over 2, from the leftmost edge, and again, the sine there is going to be of 90 degrees. The angle here between R and R and the force is just 90 degrees. And then on the right side, what do we have? On the right side, what do we have? Equals. This normal force doesn't produce any torque here, and neither does the wall's force, because those are both applied at the pivot point. So the only other force producing a torque is the tension. So the tension's torque is the force itself, T, times the distance from the pivot point where it's applied. So it's applied the full length L away from the pivot point. And then we have to multiply by the sine of the angle between those two things. So this is going to be the sine of 25, because 25 is the angle right here between the tension arrow and the position arrow of the force. The force is applied at a position shown in blue. The angle between the blue line there and the tension, also now in blue, is 25. Okay, so if we look, we see that every single term has an L in it, so we can just cross out the L's. There's an L in that first term, in the second term, and in the third term. Those cancel out. And then we simply solve for t. You're going to divide both sides by the sine of 25, and when you do, what does t come out to be? It comes to about 406, 405.8 newtons, or about 406 when we round for sig figs. All right, that's part A. Part A said find the tension, and we have done that. Part B says find the normal force of the ledge on the bar, the normal force. So the way we're going to find the normal force, Fn, is using translational equilibrium. The up forces have to balance all of the down forces, because on the whole, there's no up or down acceleration. The thing doesn't move at all. It doesn't even have velocity, so definitely no acceleration. Okay, then what points up? It's the Fn, normal force, plus the y component of tension, which is t sine the 25 degrees. And what points down? There's two forces pushing down. There's the weight of the bar, and then there's also the weight of the block attached to the end. So we know the value of t. You plug in a value of 405 right here for t. You solve for Fn, and what do you get? It comes out to be, with 3 sig figs, it's 24.5 newtons. And so that's how you solve part B.